It's a great pleasure to have Gilles here, and maybe for those of you who are in planar maps and have learned about planar maps and see Gilles for the first time, it will be the standard experience where you see the standard Schaeffer bijection, and then here stands a young guy, and that's the Schaeffer of the Schaeffer, Corey, Wauquelin, Schaeffer bijection. He'll talk us about the alpha orientations of plane maps with geometric interpretation.
Thank you very much for the organizer for being here and for the nice introduction. So my message today can be summarized as there are other bijections also. Okay, I used a lot of pictures and slides from other people, so I thank them also. And today I will discuss alpha orientations, and more specifically I would like to discuss some nice structures that are associated to these alpha orientations. And when I prepared my talk, I had this long list of examples, and I was thinking I will discuss the last one, which is the one I'm working now on. But then in the end the talk will concentrate on these two middle ones, because in some sense I think these are the most interesting to study from a probabilistic point of view now, because they are the one on which we have the most interesting results currently. So I will concentrate on these two ones. But first I need to recall you what are orientations on maps. So an orientation of a plane map is just a choice of an orientation of each edge of the map. So I won't define again maps, because this has been done a lot of time. And I will just stress the fact that I call them plane maps because I usually view them as embedded in the plane that is with a rooted outer face, and this will allow me to talk about clockwise and counterclockwise orientation of cycles in my graphs without further notice. So this little alpha in alpha orientation refers to the fact that we classify orientation according to their out degrees. So what I call the out degree is just the number of outgoing edge from a given vertex. So this vertex has out degree 4. And given an application that associates to every vertex of the map an integer, a non-negative integer, we call an alpha orientation an orientation such that the function alpha prescribes the out degree at every vertex. So these alpha orientations have been studied for quite some time. So you have seen them already this week in Marie Alban's talk on Monday. She was discussing three orientations in triangulation, and she mentioned actually proved that well, maybe she proved the other way, the fact that if so what I claim here is that any simple triangulation, by simple I mean without multiple edges, can be endowed with an orientation of the edges such that every vertex has 3 outgoing edges, 1, 2, 3, and the 3 outer vertices have out degree, well, 0 if I don't, okay, I start having sloppy slides. So I didn't put an orientation on the 3 external edges. So the out degree is 0 for inner vertex. If you really want to have an orientation everywhere, then you need to put out degree 1 and orient the outer cycle. Okay, so that was just to mention the fact that these orientations have already been discussed by Marie earlier this week. And another example that you probably know about is Eulerian orientations, where you consider a map with even degrees, where every vertex has an even degree, and you call an Eulerian orientation an orientation such that the out degree at every vertex is half the total degree. And then it's a classic result that a map admits an Eulerian walk, that is a walk that goes across every edge exactly once, if and only if it admits an Eulerian orientation, and more interestingly, if and only if every vertex degree is even. Okay, but in fact, you have even more reason to already know about alpha orientation. They actually go back to Prof work about spanning trees and also dimer configuration on the grid, as I will briefly recall. And for the map aficionados, because alpha orientation underlie many of the map tree bijection that have been developed in the last few years, and so you probably heard a lot of times about that. But today what I will try to discuss more at length is that alpha orientation coincide with the remarkable combinatorial structures on maps, the existence of alpha orientation. So, okay, briefly I review this just to introduce on an example some basic properties of alpha orientations. So let us start with a rooted map, and with a spanning tree of this map, and it's a classical result that you can on the dual map, the map which has a vertex in every face and a dual edge across every edge of the primal map, you get a spanning tree of the dual by considering the edge that are dual to the one that are not in the primal tree. So this is a classical result, and if you orient the edges of this spanning tree toward the root, then you get almost you get an orientation, a partial orientation, and you can convert this into an orientation by working on the derived map, which is the union of the primal map in blue and its dual in green. And the way you do this is that for we already have orientations for the edges that belong to one of the two trees, and then we just need to choose a local rule to orient the remaining edges. And if we do this according to these local rules, that is, we put outgoing edges from all the little squares, then you can check that every square vertex has out degree 3 because it has two outgoing edges, two outgoing black edges, and one outgoing edge which goes towards the root of the tree, while all the other vertices have exactly out degree 1 because they have one edge that go back to the root, except for the two root vertices which have out degree 0. So in fact this this correspondence was used a lot also in to show the correspondence on the regular grid. You can restate this in terms of dimers, because on the regular grid the round vertices have degree 4 as well, so the condition that no, sorry, which one? I'm going. Yeah, okay. In general, what you get is that if you consider the unique outgoing edge from every black vertex, from every round vertex, and the unique entering edge at every black every square, then you get a dimer which and the collection of the dimer that cover the map. And this is the standard relation between spanning trees and dimer configuration on plane graphs. Okay. So this is a bijection. between a set of combinatorial structure, spanning trees, on maps, and a set of degree prescribed orientations on some, so there should be a tilde here on the derived map. And one of the fundamental properties of this orientation is that if you take an oriented cycle in the oriented map and you revert this cycle, then you get another orientation which satisfies the same constraint. Because if you change the direction of edges along a cycle, then obviously it will not change the out degree of the corresponding vertices. So from an alpha orientation, you get another alpha orientation for the same alpha. And this allows, in fact, to, so here you can see what the reversal of the cycle did on the tree configuration. And using this cycle reversal, you can move from one configuration to another, and the main result, well, a nice result is that the resulting flip graph is as a lattice structure. In particular, you can go from any configuration to any other, and you can use this lattice structure to, for instance, make random sampling in an efficient way, and that's maybe one of the first way these results were used. So in fact, this property that reversing cycles on alpha orientations yield a lattice structure is a general result which is valid for any feasible alpha. That is, if you take any map with a function alpha that you can realize, for which there exists an orientation, then all the orientations, all the alpha orientation on this map are organized in this lattice structure by cycle reversals. And you can specify, you can look more carefully at what the cover relation is and so on, and use this also to produce random sampling algorithms. So when you do that, there is a fundamental example to study, which is the case of these Eulerian orientations. So here I took an Eulerian map and represented, I should stress that the picture were done by Marie, and represented the lattice structure on this Eulerian orientation. And this Eulerian case is really fundamental because, for instance, if you try to understand why the lattice structure, you will arrive to the question of comparing two alpha orientation of the same map. And if you try to look at the difference between two orientation of a same map, what you see is that the set of edges on which they differ is exactly a Eulerian map endowed with a Eulerian orientation. So the fact that you can go from any Eulerian orientation to any other is enough, in fact, to show that you can go from any alpha orientation to any other, and things go on like that when you study these structures. Okay, so what you need to remember for this first part is that you probably already heard about alpha orientations, and that they have this nice lattice structure. So another place where alpha orientation are fundamental is in describing and generalizing these mapped tree bijections. So since the first bijections were proposed, at the beginning of the story, there were a lot of independent, small independent bijections, and people in particular Bernard Diffusy, Albin Poulalon, and Chapuis, and maybe I should have quoted also Boutier, Di Francesco, and Gitter. They work a lot in order to bring all these cases into a sort of general framework. And it turns out that there is not just one framework, but maybe 3 of them, but still it makes the picture much simpler and much cleaner. And they end up with having these, what they call master theorems, that are very general bijection that you can then implement on to recover the specific bijection for specific classes of map you are interested in. So some of these bijections are based on mobile, others are based on blossoming trees, as the one Marie presented earlier this week. But most of them rely on orientation as a basic ingredient. And in fact, they require orientations that are more specific than the one I discussed until now. They require this orientation to be without counterclockwise cycles, to be minimal. That is, they consider among all the set of alpha orientation of a map, they specialize to the one which has no counterclockwise. And because of this lattice structure that we had, in fact, this the orientation they look at is the minimal one in the lattice. Okay, so instead of considering all the alpha orientations that you can put for a given alpha on a map, for a given feasible alpha on a map, they concentrate on the minimal one, and they use this extra property to define bijections. But in a sense, because of this lattice structure, so they need this minimality, but the minimality they can always get as soon as they know how to define the as soon as they find the right alpha, the right type of orientation they need, then they can extract the minimal one by they just know that it exists without further work. So a very rough summary of all this work about finding bijection between maps and trees is that to find a bijection between to find a family of tree that is in bijection with a given family of map boils down to finding the right family of alpha orientation. And then you can take the minimal orientation and apply one of the master theorem, and you sort of get the bijection. Of course, there are details to work out, but that's the general principle. Okay, but that's not what I want to talk about today. What I want to talk about today is the fact that these alpha orientation, they in several cases they have remarkable, they correspond to remarkable structures that you can put on these maps. And in a sense, with respect to what we have here, there is no theory here. There is just a collection of examples, or there is just a. I will. Yeah, there is almost no theory. So the collection of example includes these 5 ones, and as I said, I will concentrate on 2 of them, which in a sense we understand better. So I should say 3 of them. The first 3 are the ones that are most understood. The first one is considering map endowed with spanning trees, and this one I will not discuss because a lot of work has been done already on this. And the next 2 examples have been overlooked maybe, and probably I think should be interesting to study from a probabilistic point of view. Let's start with 3 orientations and Schneider rules. So again, this is the example that was mentioned by Marie in the first day. So if I take a simple triangulation, I can undo it with the 3 orientation, and again I did not orient the outer edges, but every vertex apart from the 3 outer vertices have out degree 3. Okay. But I won't require any more that this orientation is minimal, so I'm looking at an arbitrary one. So what I can do is, starting from a given vertex, say this one, I can try to follow path from this vertex to the outer vertices, and when I start I have 3 choices. And once I decided where I go, I continue by using the middle walk. That is, when I arrive to a vertex, I have 3 edges that I can use to continue, and I always take the middle one. Okay. So when I do that, it turns out that I cannot create loops. So if I do it on the example, I have one path that goes to this angle, one that goes there, and one that goes there. And in fact, this is not casual. It will always be like that. The middle walks that I create like that are self-avoiding. That is, they cannot make loops, and also they cannot intersect the 3 paths that you create. And this follows just by simple counting arguments using Euler's formula. So then you can play the same game from another vertex, and it will create other path. And of course, if you do that from everywhere, so because I said that the path cannot intersect, what I get is that I get tree-like structures. I get a decomposition of the triangulation into 3 spanning trees of the internal vertices. So I have a red tree which is rooted at the top vertex, a blue tree which is rooted at the left vertex, and a green tree which is rooted at the right vertex. And more precisely, you can check that at every, just by definition, by the fact that I use these middle walks, at every internal vertex I will have this configuration, a set of a blue, a green, and a red edge, and then incoming blue edges are in the opposite corner to the blue outgoing edge, and so on. So such a partition of the edge into 3 colors that satisfy this local condition is called a Schneider-Wood, and you can check that just requiring this local condition implies all the rest, that you will have a decomposition into 3 trees. So one could try to look at the lattice structure on this orientation. So if you take a cycle and you try to revert it, then you should get another configuration, and you can look at how it changes the tree structure. And we know, in fact, that because of the general result about the lattice structure of alpha orientation, we know that, in fact, these Schneider structures on triangulations are endowed with a lattice structure, and there is a minimal one and a maximal one. And in fact, if you look at what you have to do, the flip relation is flipping along triangles is enough. Okay. What's next? Then there is this beautiful result by Schneider, who tells you how to use this Schneider's decomposition to produce a picture of the triangulation. So what his idea is, it's just to say that from a given vertex you have 3 paths going to the 3 outer vertices, And these three paths, they decompose the triangulation into three regions. And you just count the number of faces into each region. So in the blue region, which is opposite to the blue path, you have 2 faces, 4 faces in this one, and 3 triangles in this one. And so to the vertex A, I give coordinates 4, 2, 3. I give coordinates according to this number of faces. And if I do that for every vertices, then they all get in a common plane with coordinate x plus y plus z equal 9. And if you put these points at these coordinates, you can produce 2 nice geometric pictures. One is just that I'm looking here at this plane x plus y plus z, and in this plane I've placed the vertices at their coordinates, and I've drawn straight edges between them according to the triangulations, and it turns out that the picture is a correct drawing of the original triangulation. So I should stress here that when I started here, I only had a combinatorial structure, right? I just had a structure describing me for each triangle, which are the neighboring triangles, or maybe just the graph structure of and this Schneider coordinates give me a way to actually produce a picture in the plane, to give a geometry to the to the graph. And there is this other representation which is nice also, where the white vertices are placed in the same way as they are here. They are just in the plane x plus y plus z. And then I I created a surface, a 3-dimensional surface out of these point positions. Just for every vertex going in the 3 coordinate directions, as long as I can, until I reach the plane in which lie the father of the vertex in the tree, and then when I reach this plane this coordinate plane in which lies the father of this vertex in the red tree, then I bend and make another edge. And if you do that, you can show that so the original points, the white ones, they are coplanar by construction, okay, and on top of this plane you build this surface, okay, and it's in a sense canonical in some nice way, as was first explained by Ezra Miller, and in fact this construction extends to more general cases, but I will not discuss it anymore. Okay, so let me just try to convince you that this when I do that, I get a planar drawing. So the way I can try to do that is by trying to compare the position of the coordinates that the vertex get to the coordinates of his father in one of the tree. Okay, so if I look at the edge, the green edge outgoing from vertex V, it goes to his father in the green tree V prime. And if I look at the way the regions are organized, I see that in particular the green region associated to V prime is strictly contains the green region associated to V. From the combinatorial point of view, I mean here, the set of faces that are, and so on. So, and I have similar relations for the other coordinates, and this implies that a given edge will always be, so for instance, the oriented green edges will always lie in a well delimited angle, well delimited. So the green edges all lie between this horizontal and diagonal line, and similarly the blue lines are all oriented. In a sense, they are the geometric realization respects the intuition that we used at the beginning to construct the triangulation. So the real proof boils down to a case analysis. You just say, suppose that you have another edge that cross it, and then you look at it and you see that you get a contradiction. Okay, so that's a good place to show you some picture. So we could ask this question: does this drawing gives a reasonable geometry to a uniform random map? So in order to see this, we make a picture. Okay, my mouse doesn't work anymore. Okay, maybe because it's not on. Here it is. So this is a small example of what you get when you apply to a random triangulation of size 2000. And in this example, I took the uniform distribution on triangulation without Schneider structure, okay? And then I used the minimal Schneider structure, the minimal alpha orientation, which is used for the bijections. And then I made this, I represented the drawing using this minimal angulations. And you see that when you do that, you get a geometric embedding of a uniform triangulation. So you could ask whether this this corresponds to the geometry that we expect to have. So we try larger examples to see what happens. Okay. So yeah, I should have shown you that to convince you that these are trees. I can remove one of the. I can keep only the red tree, or the blue one, or the green one. But you see that. So you have this. In this embedding, you have these very long edges and this sort of seemingly recursive structure. But of course, it cannot really be recursive. You get the impression that maybe there is a triangle that contains a lot of vertices. But we know that this is not possible, because we know that a triangle can only separate something like n to the 2/3 vertices. And if we really want to have a separator, we know that we need n to the 1/4 vertices in order to do that. So it should say that that this region, when I do like something like that, I have the impression that I can almost close the triangle, but in fact it's not really true. When I do that, I need in some sense to have a non-trivial distance here, and you can see this indeed. So if you look, before I do that, if you look at the position that the vertex are given, you start to see something like you have this. It's like a cross, but there is this apparently recursive structure. But this is just an apparent. If you try to look at okay, we can do a bigger example. So we keep this this apparent recursive structure and these. Oh, you don't see anything. Okay, so you have this little cross-like structure which recursively appear. Okay, it's not visible, but it corresponds to the triangle that you see here. Okay. So what you can try to do is you could try to follow the the leftmost path that Marie was talking about in her talk. So she said that she had these leftmost paths that are almost geodesics. So you could say one way to check whether this geometry that we have here reflects the underlying combinatorial geometry. We can look whether this path looks like geodesics. So in order to do that, you have to choose a vertex somewhere. So here is my vertex. I choose this one, and I start to follow the leftmost path. So just that there is this convention that I always mess up, and so I follow the rightmost path. And it's important because when you take the minimal triangulation, it gets twisted in one direction, and in order to get the geodesic path, you need to take the direction coherently with. And so I choose the wrong convention. So I have to take the right path in order to do that. So I do this. I try to follow this. So what I did is I took the blue edge that goes to the root, and then if you think about it, the rightmost path means I have to change color every time in a coherent way. Okay. So I take the blue, then the red, then the green, and you see that my embedding will lead me to turn around. And that's actually what happens if you look at it. So you go up to there, and then you turn again, you go down, you turn again, you go back here. And so that's what I said before. You have the impression that there is a triangle, but if you start from a point and do these 3 steps, you know that you end up somewhere far away. Okay? Because otherwise you would violate this idea that you cannot divine things. So this geodesic is really not what you would call a geodesic in this picture. Okay, the embedding takes the geodesic, the graph geodesic on my picture do something like that. Okay, so it's not, from this point of view, you could say that this is not a reasonable representation of the geometry we expect. So it's a pity. Okay. So it's a pity. It means in the sense that, okay, it's maybe not the right way to study uniform triangulations. Then, so why did I bother to explain this to you if my conclusion is that it's not an interesting way to represent the geometry? Well, the reason is that we can do more about through orientation in the general case. So let us try to go back to arbitrary through orientations. I claim that you can count these things by doing the following construction. So you take the dual, and you look at one of the 3, so say the red one, and I highlighted the edges that belong to one of the 3. And then I will cut these edges, and I will draw the binary tree that represent the matching of these edges. So this is a binary tree, which is up there, that represents the matching of these edges, and what remains in black is also a binary tree, because I started from a triangulation, and so the dual has cubic vertices, and so what I get below is the binary tree. So I can try to separate these 2 things and encode them. So for this binary tree, for this matching, I use just the standard encoding by opening and closing parentheses. And then for the lower one, I use less usual encoding, which is based on, for each position, for each region between 2 leaves, I go to the bottom and I look whether this region is a left-hand side subtree or a right-hand side subtree. And I put symbol 1, 0, 1, depending on that. So if you do that, what I claim is that you get first it's an encoding, so you can recover the original structure out of these two words. And so it's clear for this one, you all know this, that I can recover the matching out of this string. So this is a little bit more tricky, but not so much. And moreover, the two are combined in a nice way, meaning that they form a non-crossing pair of paths. There is the black one is weakly over the yellow one. And this is a bijection, and therefore, in fact, you can actually using, for instance, Gessel-Vienno's approach, you can count these non-crossing pairs of Dieck path, and you have an explicit formula for the number of these things. So it means that what I'm saying is that if I come back to what I started with, I say that the total number of all the Schneider structures on all the triangulation of size n is given by a nice explicit formula, and we can actually construct it because this is something we understand pretty well. And also there is even further information, which is that the bottom Dieck path is just the encoding of of one of the three trees. Okay. Okay, so I've shown you several incarnations of several geometric realization of these three orientations. So the three orientation, the Schneider woods, the Schneider drawing, and the orthogonal surfaces. There could be more. There are more ways to use this structure to make nice picture, but I will stop there for that. But and then I shown you that there is this bijection between the set of all Schneider woods of all triangulations, which people sometimes call realizers. A triangulation endowed with a Schneider wood is called a realizer. So the set of all realizer is in bijection with the set of non-crossing Dieck path. So this means that the uniform distribution on this set of realizers might be tractable, because non-crossing pairs of Dieck paths we understand very well. In fact, you can look at the large n limit of these things, and you have pairs of Brownian excursion that do not intersect, and you can say things about that. So again, let me just show you a picture. Okay, so I start again, but this time the difference between my previous picture is that instead of taking the uniform distribution on a triangulation and then a specific alpha orientation for that, I take a uniform, an annealed model. I take the set of all realizers, and I make a picture for that. And it looks like that, which in a sense is okay. It's not very informative, but it's nice. But still, it has less. So you still have this tree-like structure, and in fact, this red tree, we know that it's just the bottom tree of. So we know it has combinatorial height square root of n, like a standard tree. And the three, all three of them have the same property by symmetry. And if you take a larger one, then you will see that you have this. You still have large regions, but you don't have this winding pattern anymore. Okay, so it's difficult to make something which is readable, but okay. So if you go instead to look at the local structure, then you see that you can okay. So we could ask some question about that. So a nice question is, of course, can we define this uniform infinite planar realizer? Study this local limit. And I will. And I have another question which I don't know about. There is always this duality between duality relation, KPZ relation between models on the on maps and the corresponding model in the plane. So this suggests the following question: what is the equivalent? What is the corresponding regular lattice model? So a natural candidate, but I'm not good enough with KPZ to say, well, this is the right one, is to take the triangular lattice and define with some well-chosen boundary condition what a uniform Schneider tree would be on that. So it should be possible to simulate this because they have this lattice structure, and you can. But of course, then the right question is what exponent should we look at in this model, because we have all these three structures that cross together everywhere. So you have to find a way to define some long distance interesting property. Okay. Okay, so that was the first example, and then there is a second example which I will be faster on. So we now try to do the analogous thing for simple quadrangulations. So simple quadrangulation, as simple triangulations, are quadrangulation without multiple edges. And it turned out that in a very similar way as you could characterize triangulations without simple edges by saying that they are triangulations that admit a 3 orientation, then a similar characterization is valid for quadrangulation. Simple quadrangulations are the ones that admit a 2 orientation. So I have drawn a 2 orientation on. So at every vertex I have 2 outgoing edges. And again, I can try to look at path and color the edges by following well-chosen path in these orientations. And I basically have 2 ways to do that. Either well, they are symmetric. I mean, I decide that I turn left when I'm on a white vertex, and what you should do is you should alternate between white and black vertices, turn once left and once right. And if you do that, you can check that you automatically undo your quadrangulation with a partition of the edges in 2 colors. And it turns out that the 2 colors both form trees. And again, it's a simple consequence of the fact that if you do it this way, then you can count into region. If you assume that some edges would cross and count faces in this region, you see that you cannot have. So and then there is the symmetric way of doing it by turning the other way around. So from from a 2 orientation of a quadrangulation, I get 2 dual, in a sense, decomposition into 2 trees. So what I say is that this is really a separating decomposition, in the sense that it's very different from what I had on Schneider woods, because Schneider woods would cross everywhere. Okay, at every vertex, the 3 tree would cross. So this structure is behaving the opposite way. The 2 trees never cross, and they so never cross that you can actually draw the line that separates them. Okay, so what I try to do is, locally I know that they don't cross, so I start from somewhere, and I start to separate, and you can check that in every face you can only have 2 angles, which are the face of degree 4 and a finite number of configuration. You check that you can only have 2. So you can actually separate these 2 trees like that. Okay, and you could say locally nothing prevents me from doing cycles, but I cannot have cycles just because I know that I have 2 trees. So I know that the pink one is a connected structure and the green one also, so I cannot have a black cycle. And then again, you do something which is a little bit miraculous. You give a geometry out of that, And how do I give the geometry? I just use the line to give coordinates to the vertices. Okay, so the first one I give 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I get some abscissa, and then I remember that I have a second one, the dual one, and the other orientation. So I do the same for the other one. I get another set of coordinates. Okay, and every vertex gets 2 coordinates, and you make a picture of that, and it turns out that it's a planar picture. That is, if you put the vertices at the coordinate that you have computed this way. So, for instance, this guy has abscissa 6 and ordinate 5, so it should be this one. Okay, and I've drawn edges according to the graph, and what I get is it's a theorem. I get a planar embedding of the graph. So I should mention that almost all the results, I forgot to every time say who was the author. I'm not the author of most of these results. Okay, if you go back to the slides, you will see who's the. So this way of doing this embedding is due to Bernardin Fusy, and in fact, it is equivalent to an algorithm that was already known to embed these results. But this nice presentation in terms of separating lines is due to Bernardin Fusy. And actually, since the ordinates and abscissa are all distinct, what I really have here is the diagram of a permutation. And these permutations are closely related to what are called Baxter permutations, which were actually enumerated a long time ago. And it tells us that because it's known that Baxter permutation can be counted, then it suggests that these things can be counted as well. And indeed, you can count them, and you can do it in a bijective way. So I present one bijective way to do it, which consists into, again, trying to encode one of the 2 trees. So I concentrate on the blue tree, and I break all the red edges. So you can check that, in fact, you don't really, you can distinguish between 2 types of red edges. Okay, there are some details. I will skip this because otherwise. And then you encode the tree. So you have a first path which encodes part of the blue edges. Then you make a second path which completes the encoding. So it's not exactly the usual contour encoding because my tree is bipartite and I need to know which are the black and the white. So I have to refine the standard contour encoding. And instead of having 1 path, I get 2 of them, but it's not really very different. And then I need to add a further information to remember the red edges out of there, and this gives me a third path. And the result is that these the set of triples of paths that you get are non-intersecting paths, which go from some 0 point to ij, where ij really corresponds to the number of black and white vertices in the original quadrangulation. And in this way, we recover, on the one hand, a result about this formula was obtained by two different Baxter. One found it by studying some bipolar orientation of map, which is really equivalent to this by functional equation and generating series, and the other one was interested into these Baxter permutations. And in fact, you can check that that there is a relation between this part of the talk and the previous one, because if you constrain the top path to be a stair, a simple stair, staircase. Then you get that the other two paths become Dick path, non-intersecting Dick path, and we recover the formula for the previous case. And indeed, you can check that if you take a Schneider structure, you can out of it build a guy like that, which has the third part, which is really a stair, and you can recover the Schneider enumeration from that. And also, you have other proofs of this result, other bijection. In particular, there is a nice one which is based on these blossoming tree ideas that Marie discussed on Monday, which actually is maybe even simpler than this one. And so again, the conclusion is that these structures also have enough combinatorial interpretation structure that you can try to study their probabilistic properties. Now, I should have shown pictures of this one, but I forgot to put them on my computer. So Eric Fusy has nice pictures of random large random objects like that you can get. And in a sense, you have a very similar situation as what you have on triangulation, that if you take the random triangulation and undo it with the minimal structure, then you get something which has this sort of recursive structure a little bit. But again, the geodesic paths have to wind around. Whereas if you look at the uniform distribution on these two orientations, then you get something which is apparently a more sensible geometric embedding for this annealed model. Okay, so the conclusion is that there are other such nice structures. Why in the end did I concentrate on these two or three? Is because from the combinatorial point of view, so there are very nice geometric interpretation here as well, but there are no known formulas for the enumeration of the total number of maps under these structures. So it's probably more sensible to start studying these models. Okay. Thank you.
Questions, remarks? Yes?
So for triangulations, you have this formula, which is a 2 times 2 determinant in terms of Catalan numbers.
Mm-hmm.
Is this type of structure also appears in ordinal models?
You mean this type of formula?
Yeah, so I guess it comes from the fact it's non-intersecting.
So of course, if you take larger sets of non-intersecting paths, you get these kinds of formula, of course.
Does it correspond to interesting?
No, not that we know. So as I said in the end, whereas there are so many formulas for map enumeration, until now there are not many formulas for the total number of alpha orientation of a given type. So mainly there are these three. The one for the alpha orientation corresponding to spanning trees, the one for these backstuffings, and Schneider ones. And they involve this determinant in these three specific examples, but there is no general theory or generalization of that. There are generalization of these structures, and in particular I should have mentioned that the Schneider rules for triangulation can be extended to 3 connected maps, and Bernardi and Fusy have in fact a much more general definition of Schneider rules for deangulations, but as far as I know, there is no corresponding enumeration formula, and so it's probably harder to study in the first place.
Do you have an intuition of to sample triangulations, not with a uniform layer, but with a triangle width on it. So the scaling is going to be the same, or like n to the 1/4, or do you think it's going to mess?
Well, what do you think about spanning trees? If you take yes, a uniform structure map with a spanning tree. You take all the map with a given distinguished spanning tree, and you take the uniform measure on that. Then you expect to get something different, I think. And I believe you will also get something different here. I'm not able to say whether you will get the same thing or not. I don't know. You can look at the exponent. Since we have formulas, we can look to the first natural counting exponent, and they have simple. So I guess this one has the same as this one, maybe, and there is a factor n difference with this one. But then you have to pay attention that there might be some routing consideration to take into account before you say that these are really different exponents. Also because unlike what we have for models of maps, these models are not completely symmetric. I mean, the root plays a special role. The root face plays a special role. The structure is oriented toward this root. So it's, at least in the first time, it seems more reasonable to try to look at discrete model than the global one. Okay. And yes, it's really a question that maybe Bertrand could answer. What is the right regular lattice model, and does it allow to say something about exponents?
I'm wondering if there's any kind of decomposition approach to the enumeration of these things along the lines of the Polytechnique.
So, of course, I focused on the bijective way of deriving things, but yes, you can always say that if you have a pair of non-crossing paths, then you can just build these things layer by layer, well, column by column, okay, and then you will have equations for that, and it will correspond to some weird way to construct the quadrangulation. So what you will see is that since you have only a part, maybe I should have stayed there. Since you have only if you cut there and you constructed only the first part of the path, then you can already say that what you did is that you constructed only a part of the tree. So the red tree you have constructed until a point. So you constructed you take a vertex and angle there, and what is on the left you already constructed, and what is on the right you didn't. And in some sense you can say which are the edges of the triangulation that you have already done and which you didn't. So yes, you can do things like that. But okay, I don't know if this can be used easily. The equations are a bit more messy than that you get in the usual map cases, because you need two variables instead of one when you write the decompositions. But
yeah, I think we're running late, so thank you again, Gilles, for the